And he will talk about something which is a little bit complementary to what we have heard up to now, that the high density region of baryonic matter from the point of view of perturbative QCD and how this impacts on the neutron star physics. Okay, so may you start?
Yes. Okay, thank you very much for the introduction. And indeed, what I'll be talking about is a little bit different than probably most of the other lectures in this lecture week. So I'll be talking about perturbative QCD at high densities and lecturing about the fundamentals of how one performs calculations like that, and also why I'm interested in performing things like this. And I thought, both since some of this will be rather technical and also because it's so different from everything else, I figured I would start with a sort of a long summary and overview, and to give you a big picture of why I'm doing this and how everything fits together, so that as we get into the second part, the longer detailed part of the lectures, hopefully some of the ideas and physics that I described in the first part of this will stick with you and help you understand more of why I'm interested in these things. And throughout this, I don't know how interactive the other ones have been, but please feel free to ask questions or interrupt or anything like this if anything is unclear or if you want more details, and I'll do my best to expand on things. So for the very big picture, let me start with the phase diagram of QCD matter as a function of temperature and baryon density. So neutron stars live at very low temperatures, effectively zero temperature. From the point of view of QCD matter, they're completely cold, and the temperatures that they have, although they're hot for humans, are very cold for the point of view of QCD. And so for all of this, I'll be talking, well, the framework that I'm describing also works at non-zero temperatures, but when I actually get into calculations and the calculations that I use and perform in order to constrain neutron stars, I'm always doing things at zero temperature. So just keep that in the back of your mind. And there's certain regions of this phase diagram where things are very well under control. For instance, along the temperature axis at zero density, lattice QCD calculations work great and can essentially just compute the equation of state, for instance, along this temperature axis and see hadronic degrees of freedom changing into quark and gluon degrees of freedom as you go up in temperature. And in terms of the interesting regions here, we have hadronic matter at lower temperatures and densities, and quarks and gluons become liberated at higher temperatures and densities. And we know from lattice QCD calculations that the way that this transition happens along the temperature axis is a crossover. So things change very smoothly from one to the other. But in terms of non-zero density, the lattice can tell us something a little bit off of this axis, but there's no hope anytime soon of getting down here to neutron star densities at zero temperature to get a first principles calculation of how this phase transition proceeds. Many people think that there's a first order phase transition, but in terms of first principles QCD calculations, we don't actually really know how this transition proceeds. And neutron stars probe this very interesting region where the densities are perhaps high enough to start leaking over this transition, as it were, but we don't know 100% for sure. And that's why we're interested in studying and looking at neutron stars from a QCD perspective, at least, to learn whether how the equation of state behaves through this phase transition region, or at least much closer to it than we can get on Earth, or even computational. So in terms of perturbative calculational frameworks, at lower temperatures and densities, when hadrons are the degrees of freedom, there are calculational tools available, for instance, in the form of chiral effective field theory, where we have hadrons as the degrees of freedom, and they exchange pions and interact with each other. In this perturbative framework, we can calculate the equation of state, for instance, or other properties of this matter. And this, of course, breaks down as you get too close to the transition region, because that's where hadrons are no longer good degrees of freedom. Similarly, at very high temperatures and densities, we have perturbative QCD techniques that are available to us when quarks and gluons are the degrees of freedom, and they are interacting weakly at high densities or high temperatures because of the asymptotic freedom of QCD. And so one can understand something about very dense or very hot QCD matter from doing calculations in this perturbative QCD framework. And the point of view that I take is that it would be interesting to combine as many theoretical frameworks as possible to try to constrain this region in between. So if I'm talking just about the zero temperature axis now, and if I sort of show you what that other figure was displaying, but on the temperature, for the equation of state, pressure as a function of energy density, there's this region down here at low densities, which I've called nuclear here, but it's actually the chiral effective field theory equation of state. And there's a region up here at high densities, which I label PQCD, where this is the perturbative QCD equation of state. And neutron stars lie somewhere in the center here, depending on their masses. And the knowledge that I want to use is the fact that the equation of state of this nuclear matter, as you keep increasing the density, it has to, at low densities, fall inside of this equation of state from chiral effective field theory, since we know that the calculational framework works and is well behaved there. It's going to do something in between where we no longer have calculational control. But then again, at very, very high densities, theoretically high densities, much higher than anything inside of a neutron star, we know that the equation of state again has to fall into this PQCD band. And so I'm interested in knowing, is there, can we use the constraints at high density and low density and sort of fill in the center in some way, perhaps using, for instance, interpolations of equations of state to see what the allowed behavior in the middle is. So the framework that I've taken in the past primarily is to use a model, sort of like a particular type of an equation of state with many free parameters. For instance, one that I've been using a lot lately is in between the nuclear and perturbative QCD regions in chemical potential, picking some speed of sound points between 0 and 1. I'm a typical high energy theorist, so I'm going to be setting a lot of constants equal to 1. In particular, the speed of light is going to be 1 throughout this talk. So when I say speed of sound equal to 1, I mean speed of sound equal to the speed of light. And you'll also notice a lack of like the H bars and KB when we get into temperatures and things like that. But I'll try to mention that again when I show equations with them missing. So we pick some speed of sound points between 0 and the speed of light squared, and connecting them with straight lines is one type of equation of state that I've been using a lot lately, because it has a continuous speed of sound, but it's still simple enough that integration routines and things are quite efficient with it. If you integrate this twice, essentially, you get some equation of state that goes between chiral effective field theory and perturbative QCD. And I want to point out that this is really a three-dimensional matching. So these figures here are two-dimensional, but I'm requiring that the energy density, the pressure, and the number density match both at the chiral effective field theory equation of state and the perturbative QCD equation of state. So this is really a full thermodynamic matching. And so it's really in a three-dimensional space that this matching is proceeding. And that means that it ends up being more restrictive than you would naively think by just this two-dimensional picture. The idea is that I generate a large number of possible equations of state by picking random speeds of sound, random matching chemical potentials to find out what the equation of state can actually do in between. And what I find is something like this in the cyan region here. This is approximately where the real neutron star matter equation of state has to live in this equation of state plane. And this is actually without any astrophysical constraints yet. So this is just from thermodynamics and this interpolation filling everything in. And there's actually been a paper in the last week or two, I forget if it was this week or last week, that did this even more generally than I just described. So what I just talked through was using a large set of interpolating equations of state, but this new paper from this past week or so sets these non-trivial constraints just using thermodynamics itself without using any interpolations. And they do that by describing what the boundary equations of state have to be like in order to fulfill all of these constraints. So they really have these analytic expressions for the boundaries of this region. So they can't just pull an equation of state out of the center like we can with interpolations, but they can say what the allowed, the full range of allowed behavior is in terms of, it's actually a little bit larger than this cyan region. So this is why I'm interested in perturbative QCD and applying it to neutron stars. So, and why I'm interested in improving perturbative QCD at high densities, because just as others are very interested in improving nuclear matter calculations at low densities in order to have this region extend higher up in density, I'm interested in seeing if we can get this perturbative QCD equation of state more well behaved at high density, so I can use it to lower densities and really try to sort of attack neutron stars from both ends in this equation of state plane. So now let me say a little bit about what perturbative QCD is like and what cold quark matter is like. I'm going to sort of use these terms rather interchangeably throughout these lectures. So sometimes I'll say perturbative QCD, sometimes I'll say cold quark matter, but I'm just talking about the same sort of matter here. So first I'll be very, I guess, broad brush about this. So the very basic property of cold quark matter is that it's approximately described by a free electron gas, where we have quarks and gluons as the degrees of freedom, and they're weakly interacting at high density. Alpha, the coupling constant, is very small, and so these are pretty good quasi-particles with a quark Fermi sea. So we have some, this is representing the Fermi sea of quarks filled up. Everything inside of the sphere is filled up to some chemical Fermi momentum proportional to the chemical potential of these quarks. Now there's an immediate caveat which I need to point out, and that's that there are attractive forces between these quarks. In fact, as you go down in density to lower and lower densities, this force becomes stronger and stronger and is ultimately responsible for confining quarks into hadrons. But even at high densities, there are these residual attractive forces between the quarks on this Fermi sea, and that can lead, and probably does lead, to pairing effects in high density quark matter. Now, this is an effect that is indeed present and will strongly affect, for instance, transport properties and other properties of the matter that depend on the low energy excitations of whatever the lowest energy modes in the system are. But from the point of view of the equation of state or something, this is a subdominant effect. And the reason is because the free pressure goes like the chemical potential to the fourth power, and the pairing contributions to this pressure go as something like mu squared times the gap, this pairing gap squared, which is typically much smaller than the chemical potential of large chemical potentials. And that means that although this is an important effect and does qualitatively change certain properties of the matter, it's a subdominant quantitative effect in terms of the equation of state. So this is not something that I'll be discussing any further in this talk, but just that's another sort of caveat to keep in mind, that if we're not talking about the equation of state, this is something that we probably want to not ignore in that case, but it's okay to ignore it here. I'll also point out that these quarks have very high momentum compared to their masses most of the time. And so usually we can ignore the masses of the quarks. This was something I'll come back to later, but that's another thing to keep in mind, and why this is really just going like chemical potential to the 4th power. Essentially, that's the only relevant mass or scale, because the quark masses are so much smaller than this chemical potential at high density. So this is the 0th order approximation, and unsurprisingly, it's not the greatest approximation. This is a very simple model. But one other thing I want to say is that since there's no mass scale here, this behavior is approximately conformal, meaning that the pressure is equal to 3 times the energy density, and the trace of the energy momentum tensor is 0. That's sort of the 0th order behavior. And now let me say a little bit about why this is not a great approximation, but it's just a 0th order one. The reason is that interaction corrections actually do matter. So even though alpha S is small, these are still something like a 20% effect at very large densities. So I'm showing here a figure of the pressure normalized by the free, in this case, it's written Stefan Boltzmann pressure. I've written it as Fermi-Dirac here. The pressure normalized by the free pressure, which is just 1 for free massless quarks, this red line. But the actual, I think this is 2-loop QCD calculation with quark masses given in this orange band, you can see that it's quite different. And in fact, even at very high chemical potentials, this is 6 GeV, which corresponds to something like 150 times saturation density in nuclear matter, so 150 times more dense than a normal nucleus or so. This is very, very dense, but it's still, the perturbative QCD equation of state is a lower pressure than you would expect by about 20%. So these interaction corrections do in fact matter. And also this alpha S parameter runs, it depends on the renormalization mass scale and is not just a constant. So this is another, this is a mass scale that will break this approximately conformal behavior. And that's what gives us this spread here in the equation of state uncertainty band at large density. So we want to calculate these corrections as accurately as we can, since we want to ultimately fold this in to constraining neutron star matter at lower densities. And that's why we're interested in treating these perturbative corrections as accurately as we can. Now, I want to say a little bit about how one can use this. So quark matter has different physical properties than hadronic matter. In particular, if you look at these 3 physical variables, things are quite different. So if I look at the speed of sound squared in hadronic versus quark matter, this slope on a log-log plot, essentially, of the pressure and energy density, this polytropic index, it's the exponent to which you raise the energy density to get something proportional or close to the pressure. And this pressure normalized by the free pressure, which again, this goes to 1 at high densities. Quark matter behaves approximately conformal in all 3 of these things. So it has a speed of sound squared approximately equal to 1/3. This is the derivative, this is the derivative of the this equation here, essentially. That's where the 1/3 comes from. This slope is approximately 1 because the energy density is proportional to the pressure, and this again goes to 1 at high densities. Hadronic models behave a lot differently. Just the easiest way to see this is on this three-dimensional visualization here. So these nuclear matter models, as you increase in density, start off at low values of speed of sound squared, but then generically climb to higher values. They also, in terms of this polytropic index, start off at larger values, more non-conformal behavior, something closer to 2.5 or 3, and then at higher and higher densities, they sort of shift closer to 1. But they also move a little bit into this three-dimensional figure. It's harder to see this direction, but you can still tell that this behavior in these nuclear matter models is a lot different from the perturbative QCD equations of state. And some work that I've undertaken with others in the past few years is to see whether we could identify where the equation of state in neutron stars changes its physical properties from this more hadronic-like behavior to this more quark matter-like behavior by looking at the physical properties of the matter. And this is kind of similar to looking for the change in behavior of lattice results at high temperature. So even though there one can actually calculate the equation of state directly, it's still an interesting question to ask, where does the equation of state switch from behaving more like a hadronic resonance gas in terms of hadrons to something more like a non-interacting perturbative QCD free equation of state, or in terms of the pressure normalized by the free pressure, which is in this case proportional to the pressure divided by T to the fourth in red here. Where does it go from lower values to closer to 1 if it were normalized the same way I was showing before? So it's looking for the change in phase of the matter from the change in physical properties of the matter. So this is work that I've been doing recently with collaborators, and we have some interesting results here. But this is just, again, to illustrate why using perturbative QCD is interesting, even though it's really at much higher densities than are relevant directly in neutron stars. So now let me turn a little bit more towards what the perturbative QCD equation of state is like and how one calculates things. So another more technical reason why I'm very interested in computing corrections is because currently we have a very large renormalization scale dependence in the QCD equation of state at high densities. We don't really have a good way to set what the renormalization scale should be. At high densities where all the quark masses are negligible, it has to be proportional to the chemical potential. That's the only mass scale. So choosing it, this lambda bar renormalization scale proportional to the mass, the chemical potential is reasonable, but what coefficient should we use? Typically one uses 2. I won't go into the reasons for that right now, but it's a reasonable central value to choose, but it's certainly not necessarily the perfect one. And often one varies this by a factor of 2 about the central value. So we pick x equals 2 and we vary it by a factor of 2. If we're at very high densities, this seems fine. We have a nice small error bar. But as you can see, these behave drastically differently as you run down in energy densities. And even I'm always using this perturbative QCD band down to where the errors are plus or minus 24%. Again, not for any good reason, but just because it's not too large of an error. But you see that the errors really start to blow up as you go below this value. And what this means is that we can't use the cold quark matter equation of state below about 45 times saturation density, which is still a factor of 5 to 10 higher than is relevant in the most massive neutron stars. Their densities are something more like 5 to 10 times saturation density. And there's hope that higher order perturbative QCD calculations might allow us to fix the renormalization scale in some more fundamental way, rather than just saying, well, it's probably 2 times the chemical potential varied by a factor of 2, because that sounds reasonable. By using something like the principle of minimal sensitivity, where one looks at the functional form of this equation of state as a function of this parameter x, or as a function of this renormalization scale, and finds the choice of renormalization scale that gives you an inflection point, essentially, one where you have the minimum sensitivity to this renormalization scale, and then varying by a factor of 2 or something about that. Unfortunately, currently, the equation of state of high density quark matter does not have a functional form that allows you to carry out this procedure. So we can't yet use any more, I guess, any more technology to fit to set what this renormalization scale could be. But there's hope that by calculating improvements, since you're going to calculate new functional forms of the equation, of like the new things that you calculate will have a slightly different functional form. There's hope that maybe by going to higher orders, you can be able to use these other principles of minimal sensitivity or other things like this. So this is, again, what we want to improve the cold quark matter equation of state, to use it down to more relevant densities. And there's hope that even possibly even small corrections, if they have the right functional form, could even be useful still, even if they're not a large numerical correction. Okay, so now let me talk about the framework for all of this. And this is really where I shift gears and start talking about how we do calculations and in these high density systems. So the framework for cold quark matter computations is relativistic thermal quantum field theory. And this is a systematic framework for calculating corrections in a series expansion in alpha S to the free pressure. So the pressure will be some free pressure, the free quark gas, like I described at the very beginning, and then corrections in terms of powers of alpha, where we calculate these pressure coefficients. There are important caveats to come on the next slide, and there's a lot of interesting violations of this simple picture at high densities, or just generally in relativistic thermal field theories. And the language for this expansion is Feynman diagrams. And the basic, I don't know what happened there, but the basic idea is that you draw a diagram like something like this, where we have these wavy lines denoting gluons, or sometimes they're curly. You have quarks with arrows. There's supposed to be another quark up here with arrows to the left. And then the points where these lines come together represent couplings between these particles. And a diagram like this corresponds to a very particular mathematical expression that will be contributing to one of these factors of P. In this case, there's 2 powers of the coupling, so we naively would expect it to enter, there's 2 powers of G for the coupling, and each of those is a square root of alpha, so we expect this to be in this alpha S correction. Now, the reason why this may look a little bit different from some Feynman diagrams, if you've ever seen them before, is that there are no external lines here. And the reason for that is because essentially what we're doing is we're calculating the pressure of the vacuum, or the energy of the vacuum, but with a non-zero chemical potential. Or if we were also interested in non-zero temperature, a non-zero temperature, and non-zero chemical potential. So we're just drawing diagrams with no external lines. I'm going to go into a lot more detail about this throughout the lectures, and looking at how this changes as the chemical potential or temperature changes. So in general, you're going to, anything you calculate in relativistic or non-relativistic thermal field theory will have both vacuum and matter contributions. So there's a part that is the same as what you would get if you calculated this diagram using your normal 0 temperature vacuum Feynman rules. And then there's another part that depends on the chemical potential and the temperatures. And usually what we mean when we say calculating this diagram is that we're interested only in the thermal parts, or the density contributions. So usually we're talking about vacuum subtracted contributions, so that we're really not interested in this divergent part that does not depend on the temperature or chemical potentials. And now, finally, the other important caveat is that in thermal QFTs, they have different long wavelength or infrared behavior with differences from what one would expect. So for instance, if one is calculating or looking at the dispersion relation of gluons propagating in a high density medium. Normally, one would think of gluons as massless particles that just propagate forever and have no mass. This is again at high enough densities that you don't get confinement or anything like that. You can also just think of this as something like a photon behaves similarly. A photon also will have this similar effect to what I'm about to describe. So in that case, what one would do is one would say, looking at the dispersion relation, you have the energy squared of the particle minus the energy squared plus the momentum squared, and you just have equals 0. And that gives you this massless dispersion relation for energy proportional to the momentum of the particle. However, there are corrections to this that one calculates in QFTs. Even in vacuum, there's corrections to this in terms of this quantity known as the self-energy, which in this case, it describes the quantum and statistical corrections to the particle propagation from both loop corrections and the medium corrections. And in this case, if you do this calculation, and I'll be describing how one does this throughout these lectures, and at the end, I will show you how this actually works. You actually find this red line instead, where the dispersion relation of the gluons, indeed, it looks approximately massless at very high energies and momentum. But as you come down in energy and momentum, it hits a non-zero energy for 0 momentum transfer. And that is essentially saying that the gluon is developing a thermal mass in the medium. And that means it also doesn't propagate as far as you expect. This is called color screening. And a similar thing happens in a normal plasma, or a QED plasma at high energy densities. This mass is proportional to the square root of this alpha S times the chemical potential or times the temperature if you're at high temperature instead. And this is really a qualitative change in the behavior from what you would expect normally. And this screws up naive Feynman diagram expansions in that the loop expansion is no longer equal to the coupling expansion. And that means that you can write down 2 different diagrams with different numbers of loops. Normally, one thinks that the number of vertices in a diagram denotes how important it is, the number of powers of the coupling. But in this case, you can write down diagrams with different numbers of loops and different numbers of vertices, but actually contribute at the same order in the coupling, especially in a certain momentum regime. Like in this case, what's important is in the infrared regime, where this momentum transfer is very small of the gluon, that this mass really starts to appear. So there are certain momentum regimes, especially in the infrared, usually in thermal field theory, where you get this breakdown between the loop expansion and the coupling expansion. And this leads to differences from the naive expectation of how the pressure contributions go. Instead of having just a simple power series expansion in the coupling, you end up having sort of a power series correction in different momentum regions. So you have one where the free quark gas is the leading part from very hard gluons in this case. And then there's another contribution that starts at order alpha S squared from this soft momentum scale is usually how we refer to it. So we usually, the jargon is that we call this soft and this hard momentum scales. And there's also a mixed contribution that starts appearing at order alpha S cubed. And I, along with some collaborators, recently wrote some papers this year detailing how this expansion goes at high densities and how to improve calculations of what the framework is for doing this. And there's an important thing to keep in mind, which is that there is not a clean split between these scales. So there's you can't draw a line and say exactly everything below this is soft and everything above this is hard. And that leads to logarithmic dependencies in each of these coefficients individually that will sort of cancel out as you add everything in one column together. So that's just an important thing to keep in mind, that the split is not as clean as one would hope. But you do have these different momentum regimes contributing. So this is sort of the big picture overview of everything. And this is also describing sort of everything I'm going to describe in this talk, but without all of the math to wade through. So hopefully this will be something you can keep in mind as we go forward. And I'm going to explain in detail now the framework of relativistic thermal field theory, and talk through how we actually derive something like this in terms of corrections to the pressure, in terms of Feynman diagrams and things like this. So now let's dive into the details. So there's going to be a lot more equations now, but I'll try not to let them overwhelm you. The first is I'm going to start talking about QCD. So QCD as a theory we frequently define it in terms of a Lagrangian like this. So very high level Lagrangian is just this first term here, where we have the psi's here are fermions, and the A fields, which you see here, are gluons. So here we have a fermion contribution to the Lagrangian, and then this is the gluonic part. The pure glue part. You see here that this F mu nu is basically something like a Maxwell-like part where you have a derivative of the fields, and then there's an interaction part between multiple gluons. You can sort of you can see the interactions by when you have multiple fields multiplying each other in the same term. So here we have two gluons multiplying each other. This goes into a term F squared, where you square this term. So this can generate terms where you have coupling between 4 gluons, or a coupling between this derivative term and this. When you square it out, gives you a coupling between 3 gluons. And then you also get a kinetic part, which is just the square of this. And that's the normal term that you'd have even in QED calculations, and gives you basically electromagnetism if you just have that term. There's also a term, this big D is a common notation in quantum field theories, where you have a derivative term plus this term here with a gluon field in it. And this is another type of interaction. You see that there's a psi bar, gamma mu, psi, and then times A. So this is a coupling between a fermion and antifermion field and a gluon field. So this is describing couplings between the fermions and gluons. And then, just to be explicit, but usually one doesn't need all of these explicit matrices, just so you can see how it works and what it looks like. The indices here are, there's a bunch of them, of course. There's the flavor of the quarks that you're summing over here, and each quark has a mass that depends on the flavor. Also, there's colors corresponding to different colors of the quarks. So this quark field, you usually have 3 colors. Red, blue, and green are the fundamental ones. And there's a matrix here that couples the different sort of flavors of gluons in this A index to the different quark colors, which are the IJ indices. So this matrix here is really telling how the colors of the gluons talk to the colors of the quarks. There's 8 different gluon colors, sort of pairs of colors, as it were, and there's 3 quark colors for each of these. So these are 3 by 3 matrices, and there's 8 of them. They're essentially generalizations of the Pauli matrices that are 2 by 2, and there's only 3 of those to SU3 instead of SU2, which is a different group. So you have these 8 matrices essentially divided by 2, just for conventions. And then these F ABCs, there's going to be, these are totally antisymmetric, and these are called structure constants, I believe. And they have these forms here. Now, usually one doesn't need these full expressions, and one instead uses these algebraic identities that are more important than the actual matrices, usually in a lot of calculations. So frequently one runs up against structures like the trace of TA times TB multiplied by matrices and then traced over. That's some number times the identity matrix. Conventionally, it's a half for one fermion flavor, or if you have multiple fermions, it's 1/2 times the number of fermions. And there's similar other expressions here for different ways that these matrices might appear in your calculations. So if you sum over the gluon colors instead and leave the quark colors free, this is gives you a 4/3 here for one fermion, and there's also this adjoint Casimir, it's called, for if you sum over the gluons, these F values, and there's 8. That counts the dimension of the number of gluons and just gives you 8. So this is, again, usually what one runs up against. So most of the talk, I won't actually be using these forms at all, but I just wanted to give you a sense of what things actually look like if one is really trying to calculate something and really needs all the details worked out. Another important thing is that usually at high densities, you don't need all the different quark flavors. So in principle, there are up, down, charm, strange, top, bottom. There's 6 different quarks. But in dense matter, we usually only use the 3 lowest masses quarks, up, down, and strange, because those are the only ones that become active for the chemical potentials that we're normally calculating. You need your chemical potential to exceed the mass of your quark before you start really having an effect from that quark. And in high density matter, that only happens for the up, down, and strange quarks. The up and down quarks, we can always treat them as massless. The strange quark mass, it's around 100 MeV or so. It's a little bit more iffy. Usually the chemical potentials that I'm working with are around 1,000 MeV or so. So it's perhaps a 10% effect. Often this ratio appears in squares, so maybe it's a 1% effect, but still you're around the point where it may be something you want to use. You may want to use the strange quark mass. And there have been calculations seeing whether the strange quark mass is important or not. Usually it's just a small correction, but there are circumstances when you need it. For instance, if you're describing high density matter that's electrically neutral and in beta equilibrium, which you need for neutron star matter, then if you have matter that's equal amounts of up, down, and strange quark, and if all 3 of those are massless, that's actually automatically in beta equilibrium and charge neutral. So you don't even need electrons or leptons at all in order to achieve this if you ignore the mass of the strange quark. It's really just from differences between the strange and down quark that where you break the symmetry between them, that you need electrons to fill your system. So that's one example where the strange quark mass makes a qualitative difference. It doesn't end up making a quantitative difference in terms of the pressure from these electrons or anything like that, but usually you want your matter and neutron stars to also have electrons, so it's something to keep in mind. Are there any questions or anything yet? Okay, well, again, feel free at any point to interrupt. We're going to start doing some of the details now. So now the principle, the main thing that one wants to compute in thermal field theory is a partition function. Just like in normal thermodynamics, one wants to compute a partition function and then take derivatives of the grand potential or free energy in order to get other thermodynamic quantities. So we start from the normal partition function that you would expect. It's a trace over e to the minus beta h, where this is the Hamiltonian if you're at just non-zero temperature. If you have both non-zero temperature and chemical potential, then you also have this conserved current that's coupled to the chemical potential here. And you just trace over it. And we say that this is equal to e to the minus thermodynamic potential. So essentially, we just are looking for the thing up here, and we want to take derivatives with respect to this. And we need a calculational scheme for how to compute this trace of this operator in a thermal field theory. So it really is exactly the same thing that we normally do in statistical mechanics, but just with fields. And the important thing to notice here that makes this very similar to other situations that perhaps you've seen before is that this e to the minus beta h term, this Boltzmann factor, is quite similar to the time evolution operator used in quantum mechanical evolution, this e to the minus I h bar t, or I h t. Again, this is one of the points where h bar has magically disappeared. And also, this beta here is 1 over the temperature instead of 1 over kBT, which is, if we had, I've set this Boltzmann constant equal to 1 also. So this is similar to quantum mechanical time evolution. And we're actually going to treat it in a very similar manner. So first of all, this suggests that maybe there's some sort of correspondence between the IT here and inverse temperature beta here. This suggests that maybe there's something to this. Also, since normally we have calculations done in Minkowski space in relativistic context where you have minus delta t squared plus delta x squared. This suggests that maybe if IT is the important thing instead of t, maybe we're going to get something like delta tau, where this is like an imaginary time something or other squared plus delta x squared. Maybe we're going to get something that's Euclidean instead of Minkowski. So at this point, this is just like extremely suggestive and like, I mean, not extremely suggestive, meaning it's extremely just out of nowhere. Maybe it would work like this, maybe it wouldn't. It turns out that things do work this way, and I'll show this as we go on. But this is really where you can first see that maybe there's some correspondence between these two things. And like in normal QFT, the simplest and most physically transparent, I would say, way to construct this partition function is by a path integral representation of the partition function by dividing up this e to the minus beta times operators into n equal pieces where this delta tau imaginary time is very small. So we're breaking up this one operator into a product of operators where each of the exponents is a very small quantity. So let me briefly, because what I want to do is I'm going to treat both bosons and fermions together, possibly in a way different than you've seen before if you've seen path integrals. And I just need to briefly mention what the properties of these Grassmann anti-commuting fields are like so that we can use them in expressions. So I'm going to first just give a quick summary of how to deal with these variables. So we're going to need an anti-commuting psi variable in order to treat fermions. And we sort of are going to define it in terms of these algebraic properties in the following way. So first of all, it's anti-commuting. So if I have psi1 and psi2, if I switch the order, it's equal to minus psi2, psi1, unlike a normal number where you just have the same thing. Notice that this automatically tells you that psi squared for a single fermion operator or Grassmann variable is 0, because you'd have to switch sign when you switch the psi's around, but it doesn't change anything. Secondly, functions are defined by their Taylor series. So another way to say this is that we're interested in like elements of the algebra over these Grassmann variables. So if we have a function of psi, if you Taylor expand that and write it out, this is defined to be just f0, which is a number, plus psi f prime 0, which is some other number. So this is something like 5 plus psi times 3. And that is just that's the full function. The reason is because if you tried to go to next higher order, you'd have tube size, which is 0. So this is just a truncating, very short Taylor series. In fact, what this means is that fermions, once you can get used to these weird anti-commuting things, all the calculations you do are actually a lot simpler because you have finite sums everywhere. You don't have like infinite sums or anything more complicated like you do with bosons. In terms of calculus things, we also define those algebraically. So differentiating just a normal number, c, like 3 or something, is defined just to be 0, and a derivative of c with respect to c is defined to be 1, and we extend this linearly so that if you differentiated c, a plus b times c with respect to c, you would get just b, coefficient of c. Indefinite integrals, which is usually all we're interested in, are also defined in a similar manner where the constants integrate to 0 and psi itself integrates to 1. So these are just algebraic ways of defining derivatives and integrals. And this gives us all the properties that we want, actually. In particular, shift symmetry is important. So if you were to integrate f of c, you would get something. In fact, here you would just get phi prime of 0. But if you shifted c by some constant, it would also give you the same thing. So this is really like a definite integral over, sort of like from -infinity to infinity or something, that doesn't care if you shift the variable by some constant number. And again, like I said, essentially all operators are defined algebraically this way. Now, I'm going to get into the path integral now, but I think it might be best to take a break before that rather than in the middle of the calculation. Does that sound reasonable to others there? I believe it's coming up.
If it's useful in your development of the talk, then it's perfect. Okay, so let's have a little break right now.
Yes, I think that's best.
Are there some questions?
Any questions?
Any questions? Or online, can you have a look whether there are some no questions? Okay, we start. We start. No,
yes.
Okay, perfect. Let's continue.
Yes. So now we sort of have all of the mathematical machinery in place that we need to derive the path integral formulation of this. And for those of you who have seen path integrals before, it will be very similar. But I still want to show it in detail because in my experience, it's something that one sees and then doesn't see again for a very long time. And that means that sometimes it's a little bit more confusing when you look at it again. And for those of you who haven't seen it, of course, it's good to try to step through it carefully. So let me now do it perhaps in a slightly different way than you've seen before if you have seen it. And if not, I think this is kind of the nicest way to do it because it treats bosons and fermions in a very similar manner. So I'm following a condensed matter field theory book, Altman and Simons, and I'm using coherent states to evaluate this path integral. So bosons and fermions are very similar here. What one does is one defines a state phi here, and this phi can be either fermionic or bosonic, so either a real number or a Grossman number. And we define it to be e to the plus or minus phi times the creation operator acting on the vacuum. So we take a plus sign if it's a boson and a minus sign for a fermion. So if you see a plus or minus anywhere, that's what this represents. You take the top one for a boson and the minus one for a fermion. But actually, you'll see that there aren't very many of those. This is actually very similar in both cases. So now what this coherent state does is it's actually going to be an eigenstate of the lowering operator. So for bosons, the way that this works is actually a little bit more complicated than for fermions. Let me try to step through it carefully here. If we take the lowering operator and act on phi, so this is a bosonic operator now when I write it this way. This is the same as the commutation between A acting on this this thing multiplying the ground state. And that's because if they're in the other order other than the one that they're actually in, if A is all the way on the right, you just get 0 because it acts on the vacuum. So I can put this commutator around here at no cost at all. If we then expand this, write out this E to the operator in terms of its power series, since that's how it's defined, you end up getting the commutation between a lowering operator and some number n of creation operators. And if you work out what that is in terms of commuting individual operators, you'll see that you essentially get n times the creation operator to the n minus 1. This n is just coming from each time you commute a pair, you sort of split in terms of one term where you have them in the other order, where you've moved the lowering operator slightly closer to the vacuum, and then the other term that you just is the one that you get from the commutation relation. And then you just do this n times essentially, and then eventually the lowering operator kills the vacuum. So you're left with one less. And then if you look at what this is, you can cancel out this n factorial. You have one extra phi upstairs than you do creation operators. So you can put back this, this exponential term that you had at the beginning, but you have one phi left over. And so this term here is just the same state you started with, but you have this one phi left over. So you really do have this number characterizing the state times the lowering operator is times the original state. So it really is an eigenvalue, or an eigenstate of the lowering operator. In terms of fermions, let me just show you this, since fermions are, I've always found that I have less experience with them. In fact, I had to read these things when I was making these slides. So if we put a lowering operator on the fermions, first of all, we have this minus sign from the e to the minus. This eta is representing the fermion Grossman variable, so it's eta creation operator. We expand, we write out what that is. Again, it's defined by its Taylor series, which terminates after just the linear term. So this here is e to the minus eta times creation operator. So this is just what the coherent state is. Now the first term, A acting on the vacuum, again, just gives you 0. This next term is going to be non-zero. You want to use this, the raising operator gives you state 1 instead of 0 for a fermion, which is the highest state possible. And then this lowering operator needs to make its way over to turn that 1 back into a 0 state again. But it has to go through this Grossman variable. So you have to commute or anti-commute this A with this eta, which gets rid of this minus sign and gives you a plus sign. So that's the reason why you need to switch the sign here for the coherent states. So you just get eta times the vacuum. Now it doesn't naively look the same, but the reason it actually is the same is because the Taylor series expansion of eta times the coherent state, again, you have this exponential term that terminates after a linear term in the power series. The second term, you have an eta times an eta. And that, again, for fermions, just squares to 0. And so this term actually, when multiplied by eta, just gives you 0. And so this really is, again, the coherent state times this number back again. So there's, you see it, you have to sort of stay on your toes a bit more when you're using these Grossman variables, but everything is finite. You don't have these summations to deal with. So it's sort of a trade-off. I find this a little bit more easy, but you have to sort of pay more attention when you're doing the calculation. So in either case, the lowering operator on the state gives you phi times the state again. And now we need these following relations in order to do the path integral. Each of these is an identity that you can derive, and especially for the fermions, it's actually not too much trouble and not very difficult. I would definitely recommend trying to verify, for instance, this second one by hand using fermions. It's not very hard, but it gives you good practice with the anti-commuting fields if you don't have it, if you don't have that practice already. So you have completeness and overlap in the measure here. So the measure is just the things that's going to occur in the path integral. For fermions, there's no factor of pi in the denominator. This zeta is just -1 for fermions, so you don't have it in the denominator. But for bosons, you have to divide by pi because essentially because the Gaussian integrals give you factors of pi. And these coherent states are what is called over-complete. So unlike in a normal orthonormal basis that you probably are used to, this would just give you either 0 or 1 if you 0 if they're different states, 1 if they're the same state. But you see here that the coherent states, there's so many of them that there's always a non-zero overlap, regardless of what the states are. And similarly in the identity operator, usually if one's summing over all the states in the system, one doesn't need to weight them in any way. But here, because there's overlap between different states, you really need to weight them in sort of the opposite way in order to get the identity and not something that is a different operator than you want. Another thing to keep in mind is that in this measure, we're going to be integrating over both of these variables and treating phi and phi dagger as separate integration variables. For fermions, this is kind of not so strange, I think, because there's actually, like, I never even defined what a dagger meant. It's sort of just another symbol here for another independent Grossman variable. Another way you can think about it is if you have a complex field or a complex number, it has two independent parts, the real and imaginary part. So you could integrate over the real and imaginary parts separately for a complex boson field, say, or you can also integrate over the complex number and its conjugate, and that's sort of similar to what this phi and phi dagger is here. So just keep in mind that these are actually independent, even though they're written in a way to suggest they're not independent. So now what we need to do is we need to write the trace of the partition function in terms of an integral over these coherent states at the beginning and final times. So first of all, we can write this trace as a sum over all elements of the multi-particle Fock space, like this. And now we insert this identity operator in between here. So we have this, we put in this phi bra phi, and then this weight function. And now what we want to do is we want to get rid of this sum over n that we started with and just turn it into an integral over phi. And in order to do that, we have to move this term all the way to the end. And then we could use the identity operator property of this sum over all n states. We keep in mind that the Hamiltonian, and thus its exponential, and the number operator also is a bosonic operator. It has an even number of fermion fields, so it's bosonic if it's started with fermion pieces, and if it only has bosons, then it's bosonic anyway. So there's no problem with moving this all the way through it. But here we have two different coherent states, which are defined by this phi variable, which if it's a fermion state, then moving this term to the other side of this phi will anti-commute the phi and phi dagger in the two pieces. And that means that you have, in order to move this all the way to the end, you have to exchange Grossman variables in the case of fermions, and that will introduce a minus sign. And so for fermions, when you move it to the end, you have this plus or minus here if it's a boson or fermion, and that means For fermions, you actually have a minus sign here. Again, you sum over this, the sum over n in the Fock space just goes away because this ends up being the identity operator at the other end, and you're left with this expression. So what this is saying is that bosons are returning to the same state in the trace, but fermions are returning to negative the same state in the trace because we had to anticommute two of them. So this is an important difference between bosons and fermions. Now that we have this starting point, we can go through and actually derive the path integral. I'm going to be following here another good book, Line and Vorinen, and we're going to insert a bunch of different identities. So first we break up this integral, or this Boltzmann factor, as I described before, into lots of little pieces. So each one of these delta taus, these are all actually equal delta taus. I'll delete these subscripts before I upload this. There's just n of them. So these are breaking it up into lots of little sort of temperature evolutions, as it were. And now we want to insert identity operators in between each of these exponentials. So I'll just show it for the first one for space here. So we insert this phi and phi n. We need a weight because these are coherent states and they're normalized differently than we might expect. And there's another integral now. And you can see that this is going to generically give us terms generically give us matrix elements such as this, where we have phi I on one side, phi I minus 1 on the other side, because we're going to define this original phi to just be phi 1, and there's going to be phi 2, 3, 4, all the way up to n, and then back to 1 again, or back to minus 1 if it's a fermion. So each term looks something like this, where you have this term here from the weight in the identity operator, and then we have this matrix element. So the first thing that we can do is evaluate this operator it's made up of creation and annihilation operators, and I'm assuming that it's normally ordered, which is the standard thing to do, so that all the creation operators are on the left and all the annihilation operators are on the right. Is that? I might have said that backwards, but no, I think that's correct. So then what you do is you act the operators that are on the right state, and the ones that are on the left state gives you something like this, where now instead of an operator with that's a function of these creation and annihilation operators, you now just have the fields. Since this is a coherent state acting, this operator gives you an eigenvalue. That's just the quantity in the state itself. Now, so this is just now a number, either a commuting, it's always going to be a bosonic number because there's an odd number of fermion fields if it has fermions in it. It's important that delta tau is small here in order to do this. So you can't just do this at the beginning where you only have this one term. And that's because really there's an integral in here that I'm not writing. If you think about it, you sort of have to evolve. It makes sense if you think, if you carry this analogy with time further. So you're sort of integrating the state from 0 to beta in some sense. So it's sort of like you're integrating an imaginary time from 0 to beta. And the Hamiltonian at different times is not necessarily going to commute with itself at previous times. This is the problem that one has when deriving a path integral in any case. And the whole reason why one derives a path integral by breaking it up into little slices is because everything is approximately constant over that one slice if you have a large enough number of slices. And that means that if you were to Taylor expand this, for instance, you would get a 1 for the 0th order term, a linear term next, and then quadratic where you'd have multiple h's or n's at different times. And then the order between those things matters. What's important is that delta tau be small enough so that these higher order, 2nd, 3rd, and 4th order terms are negligible compared to the 1st order term. And then this identity holds. But that's, again, the reason why you need to break it up into lots of little pieces. Once you've taken care of this this exponential term, the rest is sort of straightforward. So now we have this overlap term, which is not just 0 or 1, because their states are over complete. If I write, there's an exponential here, and also this term is going to give another exponential, so I'm just going to write it as one big exponential. There's this term from the original identity. There's this overlap term, which has the opposite sign, plus sign instead of a minus. And then we have this Hamiltonian and number operator term. If one then pulls out this minus delta tau and factors out the common term in this first term, you see something that looks like a finite difference that eventually, of course, is going to, well, it will become a derivative as tau gets smaller and smaller. And you get these other terms that are just, we already made from this. So then if the limit of large n, so many slices, what one has is a large number of operators in between. So let me actually just show this again. Oh, sorry, I have to start from the beginning of the slide or certain things disappear. So what we've done is we've inserted a five dagger phi at each point in time. So we have a large number of them. And we want to integrate over every value of phi at each time slice. So that's going to become, in the limit of large number of slices, is going to become a path integral over all of the different times tau, or imaginary times tau, in between the initial and final times. That finite difference becomes a derivative, and we're just left with this. The other important point is that at the beginning and ending times now, there's this constraint that we don't have in like a normal field theory where you're calculating a scattering problem. There usually we have like the incoming and outgoing vacuums, so we don't need to worry about them so much. Here, there's an important difference between bosons and fermions, where the fields, fermion fields, have to be equal to minus what they started with, and bosons end up equaling what they, at the end, have to equal what they were at the beginning. So bosons are periodic and fermions are anti-periodic. And for usual Hamiltonians, this is essentially a Legendre transformation, which, since, again, because of this similarity between tau and this imaginary time thing, it just gives us a Euclidean Lagrangian. And in terms of fields, which here I wasn't really keeping track of the x components of anything. In terms of fields, you have this expression here at the end where you have the Euclidean Lagrangian minus mu times n. That sort of just came along for the ride, as it were. And now let me just sort of summarize everything. So that was all the machinery, and these are the results. So this is similar to path integrals in other contexts, but with a few main differences, which I'm sort of summarizing here. One is that the time, quote unquote, time integral is compact. You're integrating only from 0 to beta, which is the inverse temperature. So in fact, at very high temperatures, this is a very small interval. We're integrating from 0 to something that's also small, 1 over t, if t is large, is small. The bosons are periodic here in imaginary time, and the fermions are anti-periodic. Again, that came from exchanging the Grossman variables in order to convert the trace to this path integral form. And in terms of if one thinks of doing things in momentum space, which one frequently does in these sorts of calculations, that means that bosons, so in each case, since it's a compact interval, that means you don't have a Fourier integral anymore, but just a Fourier series with discrete energies. So the energies are sort of quantized in the usual way that you get a quantized thing when you have boundary conditions. And in this case, in order to be periodic, you have to have energies equal to 2 pi n times t. For fermions with antiperiodicity, you get odd multiples of pi t. So pi, 3 pi times t, 5 pi, and negative those things. So another interesting thing to notice is that bosons, and only bosons, have a mode with 0 energy. So when n is 0, you just get that's a valid bosonic energy, but it's not a valid fermionic energy. And that means there's one bosonic mode here that doesn't vary in the time direction at all and only has spatial dependence. At high temperatures, this is usually, I think, one of the more important modes because the other energies are quite a lot higher. If T is very high, then 2 pi T is quite large. And the bosonic mode is sort of contributes a lot in these cases. And there's effective field theories that one does at high temperature of this zero. These are called Matsubara modes, of the zero Matsubara mode. And one usually refers to that as dimensional reduction. And the reason is because it's the integral, as you see, you only have the 3-dimensional integral to deal with, and this one is just constant if it's the zero mode. Now, one also has the path integral with the Euclidean Lagrangian, as I said before, and there's a few differences there. One of the nicest differences, and one of the reasons why I like thermal field theory so much, is that I don't have to keep track of whether I'm in mostly minus or mostly plus Minkowski metric, because the metric just becomes delta mu nu. And that means raising or lowering an index doesn't change anything. It's just nothing. You get no minus signs. It's very, very nice. Another thing that you need to keep in mind is that these gamma matrices for fermions, we need their anti-commutation relation to be equal to 2 times the metric. And so now that the metric has changed, some of the gamma matrices get extra or are changed a little bit too. Usually they have factors of I in certain ones, depending on which Minkowski metric convention you started with. And now the other thing, so now let me talk a little bit about high density specifically. So up till now, this is just also how one computes things at high temperatures. The high densities, if I make T goes to 0, so 0 temperature and high density, this imaginary time interval becomes infinite again because beta is 1 over T, and that means you integrate from 0 to infinity. And that means that this whole notion of whether you have periodic or anti-periodic, depending on bosons or fermions, doesn't matter anymore. Another way to see this is that the spacing between the modes was 2 pi times T. And as T gets smaller and smaller, these discrete modes become closer and closer to just a continuum integral again. However, there's this chemical potential part here, which is different, and that does affect things. So the chemical potential is essentially like an imaginary A0 field in the Euclidean Lagrangian. So if I look at the Euclidean Lagrangian, there's this kinetic term part from the free part of the fermions, and then there's this interaction part between the fermion 4 current and the gluon A mu. Now, it's important to remember that this number density operator is just the 0 component of the conserved current. So this is the number operator for fermions, and we're used to thinking about a conserved current coupled to the coupled to a gauge field, and you have some sort of covariant derivative in that case like this. But here we have something very similar but slightly different, where we have this conserved number current times mu instead of IGA0. So this means that we have something like this as a covariant derivative instead of the usual one that maybe you've seen before in terms of gauge couplings. So there's a shift in the 0 derivatives in the Lagrangian. You can think of it that way. And what that means is that if you look at Fourier space, where this derivative brings down a factor of I times an energy in terms of these Matsubara modes, now instead of I times omega n, you have I times omega n minus mu, which if I write that in terms of more similar to how it started, it's I times something like this, where you have omega n plus I mu. So you actually have an imaginary shift to the frequencies that you're summing over. Or in terms of the continuum limit, as the temperature goes to 0, that means that each of the 0 components in any integral that you do get shifted by plus I mu if there's a conserved chemical potential for those terms. So that means that you're really doing complex analysis very explicitly in your integrals at high density. One remark I want to make about the chemical potential is, since this is relativistic field theory, you should remember that the number density is not just the density of particles, but it's really the density minus the density of particles minus the density of antiparticles, because they have opposite sort of particle number. They have opposite charge. And if you have baryons, for instance, they have opposite baryon number, things like this. So that means that it's just the difference that perhaps if you're not used to thinking about relativistic things would not have occurred to you immediately. And it's an important thing to remember. It also means that this chemical potential mu, if you flip the sign of mu, then instead of, so if you have a large positive mu, that's going to drive the system to create a large number of particles and suppress creation of antiparticles. If you have a large negative value of mu, all that will happen is that you'll have driven the system to have a large number of antiparticles and a small number of particles. So it's there's nothing inherently wrong with positive or negative mu values in relativistic field theories. And also, depending on what your conventions are, depending on how exactly you derived everything, you might actually have a minus I mu here. And it's just important to remember that flipping the sign just changes particles and antiparticles anyway, basically. So this sign is actually not so important as long as you know physically which one you're trying to drive towards. So this is sort of the framework of how the whole structure of thermal field theory goes. And now I want to talk about perturbation theory. So I'm going to be talking about interaction corrections and things like that. So are there any questions on this path integral or what this chemical potential is doing, or anything that I've spoken about so far?
One question.
So the gamma, I imagine that it's some kind of Euclidean generalization of Dirac matrices, right?
Yes, yes. So what's important is normally the gamma matrices commute or anti-commute depending on whether they're spatial or temporal, right? Because you have the anti-commutation of gamma nu is equal to 2 times the metric mu nu, g mu nu. And all that's happened here is the metric has gotten replaced by delta mu nu. So now certain things that should have in Euclidean space would have anti-commuted depending on your metric conventions. Let's say we're using mostly minus convention, then the spatial gammas probably would have been giving a minus sign when you anti-commute them. But now everything is acting the same. So yes, there's certain factors of I multiplying the gamma matrices. So your gamma matrices are slightly different, but it's just because you're now in Euclidean space. And in fact, later I don't think I'm even going to put the E on there. It's just something to keep in mind if they're slightly different. So now let me talk about perturbation theory and how one calculates corrections to the free values. So if we write the action as a free part plus an interaction part, and assume the interaction term is small, we're going to expand in this interaction term. So what we start with is this is z again, the partition function. This is e to the minus grand potential, and that's equal to this path integral. So this is a bit more schematic. I'm just showing one field here, but really, of course, there's path integrals for each of the fields separately. And also the action depends on all of them. So now what we can do is we can expand in this term, assuming it's small, and keep this term unexpanded like this. And you get some expansion like this, where this is actually 2 factorial and the next one is 3 factorial. Again, this still depends on the fields, but I'm not writing it to save space. Now, one of the nice things about thermal field theory is that this is very obviously E to something. I mean, that's what you're interested in. And so what you're really interested in is the minus the log of the partition function to get this omega term. And what you need to do then is take minus log of this path integral. So it's very, in normal field theory, if you've seen that before, usually you have to talk about like Legendre transforms and things to get these connected components. But here it's all going to come out very cleanly. If you know what that means, then great. And if not, I'll show it in the next slides here. So what we're interested in is the log of this partition function. If you note here, this one term is just going to give you this free non-interacting part that you can pull out this logarithm. So you're going to, oh, sorry, I went backwards. You're going to get the log of just this free part, which gives you this omega naught. This is just the free grand potential. And then you have to then evaluate this path integral over these interaction terms. And then you have to, since you pulled out the free part, you also are dividing by the free part. So there, here, I'm just representing that by these brackets with a subscript 0, which means that we're evaluating the operator O as an expectation value over the free system like this. So it's just the path integral with the operator in the numerator divided by the path integral without the operator in the denominator. This is nice because you don't have to worry about normalization of your path integral. You don't always, you don't have to compute the whole thing. There's just these ratios like this that you care about. And now when one has a log like this, we again are treating this S interaction part of the action as small, so we expand in it. You expand this logarithm. The first term just gives you the expectation value of this SI. The next term, there's a few different things that you get. So the first is just treating this term first as small. That just gives you the expectation value of that. But the other possibility is you can get the second order term from this first thing. And in that case, you end up getting plus this SI first in brackets and then squared. And if you look at what this is doing, it's actually removing the disconnected components. So anything that's disconnected will be in both this part and will cancel out. At higher orders, you get a more complicated expression with multiple terms, but again, it's just giving you the connected components. This, maybe you've heard of the cumulant expansion, and this is essentially what's happening here. And so what this means is that the full partition function is the free partition function plus this expectation value of these terms over the 0 free part and the connected components only. The coefficients here, I believe, are the expansions of the logarithm. So the next one is plus 1/3 and then minus 1/4. I think that's the case. I'm not 100% sure about that though, because I only wrote it out this far. So now, how do we compute these connected corrections? We're going to rederive Wick's theorem, but in a medium now. So what we do is we write the free part. The answer is that we're going to introduce a source and then differentiate with respect to the source. So first of all, we have this free part, which for the purposes of this derivation, I'm going to write as an integral over 2 different spatial components of this sort of this matrix multiplication like this. Now, really, the operator that you have here is diagonal. So there's sort of a delta function implied inside of it, but it's going to be a lot clearer to do things in terms of this right now. So then what one does is one defines a partition function with a source J. And it's the sum of the first part here. This is the free part. So this is e to the minus S free plus this J times phi. And we're ultimately going to want to take derivatives with respect to this J in order to bring down phi's in front of this path integral. And now one can do some manipulations here. One completes the square. So first one completes the square of this phi a phi term here. And then that means that you have a shifted phi term in your square. And you just shift it away since what's the term for this? I'm sorry. The measure doesn't care about a shift when you shift phi. So what one finds when doing these two straightforward manipulations is that you get an exponential of 1/2 J A inverse J, and then the free path integral again. So you just get some term that has only J's and then something that has no J's. And then in order to calculate terms like this, where you have multiple insertions of phi's, a value, and you want the 0 and connected components, you just take multiple derivatives with respect to J, as I was saying before, to bring down these phi's. You can see it very directly from the starting expression. And then we set J equal to 0 at the end. And now, in terms of actually doing that, since we completed the square here, this is very simple. So the Zj is just this expression. We plug it in here. This 0 part, this actual partition function that we started with, doesn't have any sources, J's in it at all. It just goes through these derivatives and cancels this one. And then we take just derivatives of this exponential. So we expand this exponential in a series like this. And then we look for a term, since we're ultimately going to set J equal to 0 at the end of the day. We look for the term that has the same number of J's in it as the number of derivatives we have. It has to be an even number. Each one of these only has even numbers of J's. We find it, we take the derivatives, we do the combinatorics to see that all these 1/2s cancel out, or the 1/n factorials cancel out. And you're just left with all connected combinations, since we're only interested in connected components in the beginning, of the inverse matrices summed over all the different possible pairings between the phi's. These are called Wick contractions and are frequently written by writing little lines on top connecting which phi's you put together. And in terms of what each of these is, excuse me, you see that one of these is exactly what you get if you just differentiate with respect to 2 sources and only 2. So really this is just pairing things like this. And you have your original the original connected components are now the sum of all connected combinations of ways of pairing individual phi's like this. So this means that you're just ultimately reducing everything to just these simple correlation functions instead of this more complicated correlation function. Now let me just show an example, since that's a very abstract equation. It's actually very straightforward. See. So an example from phi to the 4th theory is if I'm interested in calculating the first correction to the free grand potential, I need to calculate this expectation value, SI0C. This is the phi to the 4th term is usually written lambda over 4 factorial times phi to the 4th. So that's where we get this lambda over 4 factorial term. And now if we use this Wick's theorem, Wick's contraction, this first phi, for instance, compare with either the second one, third one, or fourth one, and that only leaves 2 left over that have to get paired. So that means that there are 3 terms, 3 over lambda over 4 factorial, pairings like this, where you have 5 phi and then 5 phi again. And now this is usually written pictorially as this, where this 3 over 4 factorial is just 1/8. And then there's a lambda from a vertex, and then you have 2 of the simple correlation phi, phi. In this case, they're actually at the same point. because they go back to the same point. So it's phi x, phi x. And this is a Feynman diagram. This is, of course, you can see that there are no external lines, as I mentioned very early on. And these fundamental correlations are called the propagator. So it's very similar to normal QFT, except, so it has this form. It's very similar, except for two differences. One is that this is Euclidean p squared, so it's p naught squared plus vector p squared. And the second thing is, if this phi has a chemical potential associated with it, then the p naught component is p naught plus I mu quantity squared plus p vector squared plus m squared. A nice thing about working in Euclidean space is that you don't have any of these I epsilons that you have to worry about in Minkowski space. Of course, when actually doing Minkowski calculations, one usually Wick rotates to Euclidean space anyway. But in this in thermal field theory, you're sort of starting with Euclidean calculations from the beginning. So this is the whole framework now. Essentially, there's the path integral. There's these Wick's theorem contractions to compute corrections to it. And now the last thing that I want to discuss is the last thing that I talked about in my overview, which is how infrared limits of quantities can be different than you expect. In order to do that, I'm going to talk about the self-energy of a propagator. So the self-energy are corrections to the propagator. Essentially, like if you have a self-energy here in the denominator, they come from expanding p squared plus pi as power series, 1 over p squared plus pi. And pictorially, they're usually written as the full correlation function propagator is equal to the free. And then in this case, since I use a plus sign here, I have alternating signs of minus plus for multiple pi insertions added together. Mathematically, the expression is this, where the the full correlation function, the connected part, is equal to this phi free propagator minus the free propagator pi times the full propagator. So you see that if this has the full propagator on both sides of the equation, and you can generate this series by sort of iteratively plugging in the right-hand side, or this equation into this term here. You keep getting more and more phi naught pi, phi naught pi, phi naught pi's as you do that multiple times. And now what this means is, well, let me go back for a second. So what we want to do is now we want to calculate this self-energy for a simple system to see what happens when we have whether we have a different infrared limit, like I was saying we did at the very beginning. So what I'm going to do now is I'm going to talk about the self-energy of a gluon and look at what happens as the gluon momentum becomes smaller and smaller. So this self-energy is actually going to have a non-trivial infrared limit, and let's calculate it in QCD. So first, I'm going to rearrange that previous expression that I just showed you for the one loop gluon self-energy and high density. So I pulled the phi naught on the other side of the equation. This difference here is just, there's an interaction term in this full propagator that's not in the zero propagator. And so that means that you have this e to the minus interaction term minus 1. And that's equal to minus this the term with the propagator on the right-hand side. So this is the starting equation. And if I'm only interested in the one loop propagator at the lowest order, I can replace this full propagator on the right-hand side by the free one again. And I'm now going to also expand this interaction term again. So you see, we get something very similar to what I had before on the right-hand side, where you have two A fields now. So I'm talking about the gluon self-energy. And I have Si minus 1/2 Si squared, and then you'd have higher order corrections. And on the left-hand side, we have two free propagators connected to a self-energy. Ultimately, what's going to happen is we're going to amputate these correlation functions of these propagators on the left-hand side. And so we're going to try to pull them out on the right-hand side also, and then take them all away. So the first important thing to note is that the first order term is not enough to get you something that's different at high density. You need a fermion loop. And in order to do that, you have to have two vertex insertions because each vertex has two fermion lines and one gluon line. And we need to couple to two different gluon lines. So at high density and zero temperature, the lowest order correction comes from this term. At high temperature, there would also be a correction where you have a 4-gluon vertex, and then you would need this term, but at high density, this is the lowest order correction. Now what we do is we insert what these interaction terms are. If you go back to what I said about the Euclidean Lagrangian, and then plug them in, you'll find this. So there's two insertions of this phi bar A/phi. There's two insertions of the vertex, two vertices, so two insertions of G. There's also these matrices TA and TB, which I talked about previously for the colors. This is just a color factor, and I get this trace component because of the way the indices are contracted in here. And again, you see that this is one of the things that I said earlier. We usually are only going to encounter certain forms of these, certain algebraic occurrences of these TAs and TBs. And this particular one is just this TF times delta AB that I mentioned earlier on. And now what we want to do is I'm going to use Wick's theorem or Wick's contractions in two steps. So the first is I want to isolate these A fields in order to get rid of them. So what I do is I see that this A here, in order to give me a connected component, has to either couple to this A inside or this A inside. If I were to connect the A on here and this A, then they would be paired, the two vertices would be paired with each other, but they're not connected to the actual external A's, and it would be a disconnected diagram. So this is the only way of pairing the gluon fields to get something connected. That also gets rid of this factor of 1/2 because this A can couple to either this one or this one to give you a factor of 2. I've also introduced what this trace is. It's just it's 1/2, it's NF over 2 times delta AB. So now you see that on the left-hand side and the right-hand side of this equation, we have similar A naughts on both of them. So we can amputate them and throw them away. So now this is saying that the self-energy itself is just this contraction with some extra factors. And now in terms of Wick's theorem again, now we have to pair these phi's in some ways. And the only way to do that gives you a connected component. Wait a minute, there's supposed to be a picture there. So let me see if it works if I go back, because this makes a lot more sense. Okay, I don't know why that's not working, but there's only one possible contraction where you get something connected, and that's if you connect the one phi bar and one of the vertices with the phi and the other vertex. Essentially what you have to do is you have to put this phi all the way at the beginning in order to get two propagators. And in doing so, you have to anti-commute it past 3 different fields, which gives you a minus sign. This is sort of a generic thing that whenever you have a closed fermion loop, you're going to have to go through an odd number of fermions and you get a minus sign. That's possibly something you have heard before. I at least had heard it a lot, but I never remembered exactly how the derivation goes, but it's just moving this one all the way to the beginning. Now let me, just so you can see this picture, I guess I have to go this way. This is just corresponding to this one diagram where you have 2 propagators, this one, another one here, and then you have 2 vertices, 2 gamma matrices, 1 in each vertex. So this is just a 1 loop correction to the self-energy. Don't know why it's not displaying though. And now if we write out what these are, I never actually told you what the propagator for a fermion was, but it's very similar to the propagator for a boson. Just instead of 1 over q squared, it only goes like 1 over q, sort of like a square root of sorts. And you have this extra gamma matrix structure in the numerator. There's also this extra factor of I that's different than in Minkowski space. So you have some contraction like this. You also have a trace because you need to make sure that this final gamma, this final psi is contracted with this final gamma matrix still, even though you moved it all the way to the beginning. And in order to make sure this is contracted with this, it has to be traced over. And also now remember that the Q naught has to get shifted by Q naught plus I mu in both the denominators here, in both of these denominators and the numerators. So this is the expression one needs to calculate. So now the important thing to keep in mind is that if we're interested in the IR behavior as the momentum P gets small, inside of this integral, P is sort of the only dimensionful scale. There's the Q that we're integrating over, and there's nothing else except for this P, since I'm ignoring the masses of the quarks here. And that means that the infrared behavior of the self-energy is going to be dictated by sort of the UV behavior of this integral. So when P is much less than Q, we're looking at the UV behavior of this integral. So if we do that, we see, okay, we have the two propagators. Each one goes like Q over Q squared when Q is very large. The first one is obviously Q over Q squared. The second one, we can ignore the P when P is small and Q is large. We get another Q over Q squared. I'm also ignoring all the trace and stuff, all the gamma matrices and other factors. That actually is not going to qualitatively change this expression here. Also, this integral over Q is a four-dimensional integral over Q, so you have a dq Q cubed, and you're left with, once you cancel everything out, it's just dq times Q. So this is a UV-dominated integral that's dominated by the hardest value of Q that occurs in this loop. It's of course divergent, at least the vacuum part is, but if one does this calculation properly using the residue theorem to evaluate these complex integrals, remember, because we have the shifted components in the denominators and the numerators, one finds that doing the residue cuts off this integral, at least for the matter part, at mu. That's possibly expected because mu is the only relevant mass scale also. And that means that this integral comes out proportional to g squared mu squared for small p. So this is exactly what I have been saying at the very beginning here, where the gluon has acquired some thermal mass proportional to g squared times mu squared, or the thermal mass is the square root of this, so g times mu. This is really me squared in a sense. So this is saying that as your gluons get softer and softer, indeed, they acquire, there's this sensitivity to this mass. Now, this whole procedure of looking at the UV behavior of this integral and realizing that this expression, this pi, is being dominated by the hard loops is sort of a generic thing. This goes under the name of hard thermal loops or hard dense loops, depending on the context. This was first written down in the 90s by Bratson and Pizarski. In the cold quark matter context, Christina Manuel first used it in 1996. So this is sort of a generic thing that one does in these sorts of situations when one's interested in infrared behavior. And this shows up in a lot of contexts, not just in scattering, but as you see here also, it will show up in pressure contributions. Now, finally, let me just say a little bit about what this integral actually is. So I only showed you how it behaves in terms of like what its scales were. It ends up having a non-trivial dependence on P naught over vector P in the HTL result. So it's more than just a thermal mass. And all the components are actually like this, where I see I've left out a delta AB on the right-hand side here. So there's an ME squared in front, which now I'll finally define it. It's indeed G squared mu squared summed over all the fermion flavors with some extra powers of pi. There's also these other terms here where you have a light-like Euclidean vector. So this little v is a unit vector in R3, so its square is 1. The time component here, this I squares to -1. So in Euclidean space, v dot v itself, this big V dot big V is 0. So it's sort of like a light-like vector. And if one actually computes this, this non-trivial function of p here, you see one finds this, this function here that's a log of p naught plus vector p over p naught minus vector p. So there's this strange non-trivial structure which shows up in a lot of different places, since the self-energy is a very ubiquitous quantity that shows up in many places. You also see that this has a very particular, its trace is very simple. So if I contract mu and nu together, so I look at pi mu mu, since v dot v itself is just 0, this whole non-trivial function goes away, and you just get delta. These just become 1, and you just get me squared. So the trace of this self-energy goes to a constant, but each of the individual components depend in this non-trivial way on this ratio of p naught over p. And this is sort of generic, what one finds, that there's similar hard thermal loop contributions for general endpoint gluon functions, where if you were to do a similar calculation of this graph, where you have 3 propagators and 3 vertices, if you let each of these momenta become soft, you get a non-trivial function of the ratio of these momenta components. So this is a very complicated and interesting infrared behavior of these gauge field theories. And just to bring us full circle to what I said at the beginning, this ends up giving you these hard contributions, soft contributions, and mixed contributions, where this soft line here are really the HTL expressions. We have a 1-loop HTL diagram or 2-loop HTL diagrams in these different kinematic regions. And the state of the art now that we just did in this past year is we've calculated these 2-loop corrections, self-energy corrections. Since I'm running out of time, I won't go into detail about exactly how that's done, but I have some pictures on the next few slides that I'll just skip over now, just to point out that we have these 2-loop HTL diagrams that we compute, and that they do shift the pressure slightly. They actually decrease their normalization scale sensitivity. So the distance between the solid lines, which are the things to look at here for the 2-loop plus soft N3LO, the spread in the solid lines are smaller than the spread in the dashed lines. The different colors are the different renormalization scale choices. So it really does help improve the convergence of the perturbative QCD pressure to calculate these soft screen gluon interaction corrections accurately. And we're hoping that the mixed contribution, which is the next easiest one to do, the soft is the easiest, the mixed is the second easiest, and the hard is unsurprisingly the hardest to do. We're hoping that the mixed contribution will also similarly help decrease the renormalization scale sensitivity. So all this work is actually paying off and is helping us to understand cold quark matter even better. So just some concluding remarks, which it's not really possible to summarize everything, but thermal quantum field theory at high density, just what it is, it's a systematically improvable framework for calculating corrections with thermodynamic properties. And it has a rich EFT structure involving multiple scales. At high temperatures, there's even more interesting things that happen with different effective field theories that are really more cleanly split than they are here at low temperatures. The current state of the art for cold quark matter is this N3LO computation that we've just done this year, and it's ongoing. We're working on the mixed corrections now using this approach of kinematic regions. And just the main message that I want to convey is that from the very beginning is that cold quark matter does restrict the neutron star matter equation state at lower densities. So I'd be happy to answer any questions or review anything that I said, or go back more slowly over something if there are any questions.
Okay, so thank you very much, first of all, for this very clear presentation. Are there some questions?
Yeah, I have one, but it's quite short. It's this. I'm a bit confused about the name. For example, you say that gluons acquire a thermal mass, but you are not considering thermal effects, right? So it's probably some confusing name.
Yeah, so I am kind of weird in that I use thermal to mean like medium effects, but I guess that's true that it's not the best thing to say. So it requires an in medium mass. It's probably the least ambiguous way to say it. So it's a mass because of the medium effects, like it's proportional to the chemical potential. So if you don't have the density, if you don't have the chemical potential, it's not there. So it is coming from the medium, but indeed, yes, thermal is perhaps not the best word. And I can change that before I upload the slides.
I suppose that that name comes from the fact that if you, instead of having a finite mu, you had a finite temperature. So in the case of peak temperatures in which you have, for example, quark-gluon plasma or that stuff, then you have also this kind of contribution. But instead of coming from mu, coming from the temperature, right? So
yes, yes. Yeah, so if you were to do this calculation at high temperature instead of high mu, it would come about differently, exactly how it happens, but indeed you would have a g squared t squared instead of g squared mu squared.
So, and what will be the main difference between, for example, the dependence of the self-energy with momenta, instead of having high density, having high temperature, or is more or less the same all the way in perturbation theory?
In all of perturbation theory, it's different. It's quite different. One important difference is that you have these different discrete modes to sum over, which makes your integrals very different. So instead of a 4-dimensional Euclidean integral, you'll have a 3-dimensional Euclidean integral, and then a discrete sum over the energy components instead of an integral. That ends up making the expressions much worse. Another difference is that every single diagram will now contribute. So even if you have only gluons in your diagram, they can be thermally populated. And so diagrams that have only gluons at high density do not contribute because there are no quarks to sort of change the diagram from the vacuum. But at high temperature, those diagrams do change because the gluons are populated thermally. Interestingly, in terms of this self-energy, there is no difference. I mean, what one finds is exactly the same expression. It's just that ME, instead of having a mu here, has a T. It's very straightforward. And in fact, even the next order in the HTL expansion, so like if you were to calculate a 2-loop, oh no, sorry, this is not true. This is something that we're currently working on. The 2-loop HTL expressions are different, but the leading order HTL actually is exactly the same, just replacing mu in certain places by T.
And, another question. So it would make sense to try to do some calculations in a regime in which neither the density and neither the temperature are negligible compared with each other. Is there any physical system in which this is somewhat true? Or?
Yes, yes. So if I go all the way back to the beginning, just to show you the phase diagram again, yes. So you do probe sizable temperatures and densities during neutron star mergers or in supernovae. So in that case, the temperatures can reach something like 100 MeV or 50 MeV or something like this, which is not completely negligible compared to the 200 or so MeV of lambda QCD. So in neutron star mergers and supernova, you do have both thermal and density effects, and they're both important. And this is something that I am currently working on things like this as well. But yes, you're right that there are regimes where these both are important.
Okay, thanks.
So, are there some more questions? Online? No. Well, if there are no more questions, then I want to thank you again. So thank you very much. Okay, so I hope in some future we will have even the possibility to see you in person in another occasion, because I think here in Santiago work on some aspects of, well, high density QCD plus its application to the nuclear equation, to the baryon matter equation of state will continue. So, and for now, thank you very much. Goodbye.
Yes, thank you. I do hope to meet you in person someday as well.
Me too, but you see, right now life is quite complicated.
Indeed. Yes.
Yeah. Okay, so thanks. Bye-bye.
Bye-bye.